Hello, I'm Anna Mackay, and this video is on motion or kinematics, unlike in the last video where I called it kinetics, in the integration chapter. So we've looked at motion before in differential calculus, and now we're looking at it in terms of integration. So in that way, we are able to start with a function of v, velocity, as opposed to starting with s, displacement. So let's have a look. We've got this one example and we've got a few parts to it. A particle moves along a straight line with this formula, v for the velocity is equal to t take 2 meters per second for time greater than 0, and an initial position of 8 meters to the left of the origin. Now just to refresh on that, initial position means when t is equal to 0. So our displacement function is s. So when s of t, but when t is equal to 0, we will have 8 meters to the left of the origin, which means it will be at -8. So that will come in handy. And the first part we're being asked is to find the equations of the particle's position and acceleration after t seconds. Might be handy to write down somewhere that position refers to displacement, in case you get stuck at any point in time, and that is the s function. Let's do acceleration first because it's going to be slightly easier. So our acceleration function, if you need a refresher, is the derivative of the velocity function. So if v of t is equal to t take 2, our acceleration function, differentiating that, we end up with just 1. It's 1 meter per second squared. And the equation of the particle's position, which is the displacement function. So s of t is actually the integral of our v function with respect to t. So here we are, we're integrating t take 2, and we apply our integration rules, raise the power by 1 and put it over the power each time around. But because it's not a definite integral, we have to add the integration constant, which is plus c. So that's not the end of our function, because we would like to sort it out and find out what this plus c is. So we use this fact that was in the original question, that s of naught is equal to -8. So how we write that is s of naught, so where you see a t, you're subbing in a 0, the 0, 0 plus c is equal to -8. So then we can rewrite our function completely. That's a t. We have t squared on 2, take 2t, subtract 8. And that is our the equation for the particle's position, or the displacement function. Right, the next part. Find the particle's position when it changes direction. Have to cast your minds back, but it changes direction when the velocity is equal to 0, which means it's stopped. It's had a pause. So let's find that out. When does v of t, which is t take 2, equal 0? Nice and easy one there. When t equals equal to 2. That's not the end of the question though. Go back and read it. We need to find the particle's position when it changes direction. So this is the time when it changes direction. And so we need to substitute this into our s function. So s of 2. But before we do that, remember it was good practice to draw a sign diagram every time you get one of these. This is going to come back in handy a bit later on. For time greater than 0, refresher how to do that. We want a number either side of 2. So if 1 less than 2 is 1, substitute 1 in here. 1 take 2, that gives you -1. -1 is a negative number. So we have a negative here, and they alternate in this case, but just to double check, a number greater than 2, 3. 3 take 2 is 1. 1 is a positive number, so we have a positive sign there. Back to what we're doing, we are substituting in for t is equal to 2 into our s function, which we worked out previously. So we have 2 squared on 2, take 2 times by 2, subtract 8. Working that out, we'd get 4 on 2, take 4, take 8. which gives us negative 10. Don't just leave it there. Go back and read the question. It said find the particle's position. You can't just say negative 10. Being a negative, that means it's to the left of the origin. If it was positive 10, it would be to the right. So we answer that saying 10 meters to the left of the origin, or its starting position, if you like. Right, next part. Find the particle's position after 5 seconds. You might be wondering, why 5? If you go ahead and read, often in the questions that you're doing, read the whole question through. But in this question that we're doing, we eventually want to find out the distance travelled in the first 5 seconds. So that's why 5 is useful. So the position after 5 is S of 5. That's a 5, not an S. So substituting that into our S function. And we get, subtract 8. Feel free to jump straight to the answer here. 25 on 2, take 10, take 8 is equal to negative 5.5. So answering the question, find the position, it's 5.5 meters to the which side? Left or right? Left of the origin or the starting position. And the last part here is finding the distance travelled by the particle in the first 5 seconds. So casting your mind back to when we did motion in differential calculus, distance travelled, motion diagrams, you need to know where it starts, so S of 0, where it finishes, so S of 5, and does it change direction, and where it is at those points. So creating a visual here will be important. Remember on that sign diagram for V, either side of 2, it was negative first and then positive. And what that's going to mean is on the graph of the velocity function, it'll be below the x-axis first and then above. So one way of looking at that here is this box I've got, that the total distance, the modulus here for the first part that's below the axis, and then the second part is above. Now this concept will be new. There's a few ways to doing finding the distance travelled. In the past we always did it with using the S function, but now that we have integration, using the velocity function, the area in the section that we're after between say 0 and 2 and then 2 and 5, the area in the velocity function will actually give us the total distance travelled. So I'm going to do this a few ways. I'm going to show you on your graphics calculator, and then we're going to come back and do it by hand. So hang on, here it is. Here's our velocity function. Y is equal to x take 2. Graph that. Think about your view window. It's time, so it's always greater than 0. So we'll start with greater than 0, but we're after the first 5 seconds, so let's make that 6. And have a look at that. I think I could zoom in a little bit more, so I don't need quite as much in the Y region. Let's go negative 5 to 5. There we go. So I'm after between the 0 and 5. So you can calculate the area here. So Shift G solve, calculate between 0 and 2, negative 2. Now, you've got to get your head around these applied integration questions. This is the velocity function here. This is not the displacement, which is where this particle is. But the beauty of integration here is if you integrate the velocity function, that value of the area is the distance travelled in those first 2 seconds. It's not negative 2. It can't travel negative 2 units, or meters. It's travelled 2. And then in the second section, integrate that between 2 and 5, 4.5. So 4.5 meters in the next 3 seconds. So that's going to total 6.5 meters. Let's go back and work that out by hand. Okay, over we go. Right, I'll show you what we need to write. So you can do it with integration, but I'll just do it by motion diagram again as a good refresher. So you have to write down where it starts, where it changes, and where it finishes. So some of these, with all of them, we've already worked out, and here are our answers. And then we draw a motion diagram and we put these 3 points on in order. It doesn't matter how far apart they're spaced. It's just a rough diagram. And we started at -8, we went to -10, stopped, and then it ends up at -5.5. And so the total distance, we write, is, so think about that, between -8 and -10 we travelled 2, and then you travelled another 2 to get back there. There's quite a few ways you could set that out. And then between -8 to -5.5 is another 2.5. Don't be thrown by all those negatives. And that is 6.5 meters. So that's the total distance travelled in the first 5 seconds. And that matches with what we did on the graph by integrating the velocity function. So that's how to do a motion question. If you liked it, give it a thumbs up, subscribe to the channel. And the last video in the Integral Calculus series will be an example on problem solving by integration. Thank you.